Welcome to Gold, Cratons, and Meteor Impacts. Western Australia covers an area of 2.5 million square kilometers, which makes it the same size as Greenland. The major geological features that we will focus on are the Pilbara Craton and the Yilgarn Craton, both of which are Archean in age, as well as the Hamersley Basin, which is Proterozoic in age. So the three most important geological features in respect to us understanding the spatial and temporal distribution of gold in Western Australia are Pilbara Craton, Hamersley Basin, and Yilgarn Craton. It was Dr. George E. P. Box who drew our attention to the fact that essentially all models are wrong, but some are useful. So, acknowledging right up front that the model we are creating here is wrong, the most important question is how wrong does it have to be before it is not useful? The Pilbara Craton. This is the northern part of the Pilbara Craton. A black and white geology map is presented because it makes it very clear where the major faults are located. It becomes obvious that there is a radial distribution of the major faults in the northern part of the Pilbara Craton. The Yilgarn Craton. A black and white geology map is presented because it makes it very clear where the major faults are located. It becomes obvious that in the Yilgarn Craton, the terrain boundaries and the fault trends are radiating from a common center. Let's now have a look at the Hamersley Basin. In the Hamersley Basin, most of the rocks are sediments consisting of conglomerates, shales, and quartzites with thick layers of blue asbestos and iron. Australia's major iron deposits are in the Hamersley Basin. Let's close the Hamersley Basin and see the impact on the Pilbara and Yilgarn Cratons. Closing the Hamersley Basin. To close the Hamersley Basin requires that the Pilbara Craton be moved 300 kilometers to the south. The radial distribution of faults in the Pilbara. The fault trends in the Pilbara continuing on into the Yilgarn. The radial center. It is proposed that the radial fracture pattern seen in the Pilbara and Yilgarn Cratons are due to a meteor impact, as you can see here at a much smaller scale of the radial fractures in the Meteor Crater in Arizona, USA. At a grander scale, the radial distribution of fractures and intrusions around the Deniliquin multiple ring feature in southeastern Australia. Osinski et al., in their book Impact Earth, a review of the terrestrial impact record, make the following statements. Quote, field studies of craters on Earth reveal the degree of structural complexity that is typically hidden from view in remote sense data on fresh planetary craters. These terrestrial studies show that crater collapse occurs along a series of interconnected faults oriented both radially and concentrically to the point of impact. Concentric faults are often listric in nature and can be oriented both inwards and outwards. Radial faults accommodate movement along concentric faults, and deformation is also accommodated via radially and concentrically oriented fold structures. This is the proposed origin of the radial pattern, which is a 1,800 kilometer diameter meteor impact. This is the location of the radial center on our satellite map of Western Australia. This is the proposed meteor impact, which has independent confirmation. That independent confirmation comes from Johnson et al. 2022 from their paper titled Giant Impacts and the Origin and Evolution of Continents. They propose, using oxygen isotope studies, that the Pilbara craton is the site of a giant meteor impact. Johnson et al. Show that the oldest preserved continental crust within the Pilbara craton is mostly comprised of sodic granites of the tonalite-trondhjemite granodiorite series. This series is derived through partial melting of hydrated basaltic rocks, that is, amphibolites, at depths of around 25 to 50 kilometers. As will be presented below, these sodic granite intrusions are generally approximately 100 kilometers in diameter. Following is the evidence presented by Johnson et al. 2022 that the Pilbara craton is the remnant of an ancient meteor impact. That remnant was built in 3 stages. Stage 1. Stage 2. And Stage 3. Hansen, 2015, appears to be the first person to suggest that Archean cratons here on Earth have a meteor impact origin. The Yilgarn craton. This geology map of the Yilgarn craton shows the major faults and their radial distribution, but also gives names to those faults. Ivanek et al. 2010 shows the presence of what I have labeled the Meekatharra bulge. This bulge is approximately 100 kilometers in diameter and delineated by major faults. The location of the Meekatharra bulge. A careful examination of this geology map shows there are several other bulges as delineated by major faults. When this more detailed geology map is superimposed on the previous map, many more bulges are revealed. Note that each bulge is approximately 100 kilometers in diameter, and the largest of these bulges is located in the southeastern part of the Yilgarn, where the bulge is approximately 200 kilometers in diameter. This largest bulge will be evaluated in more detail later on in this presentation. Laux and Campbell, 1998, recognized what they labeled as fossil cell arrays in the Zimbabwe craton. Note that each of these gneissic plutons is approximately 100 kilometers in diameter. It is likely that the granitoid gneissic plutons presented here are equivalent to the sodic granites of the tonalite, trondhjemite, granodiorite, TTG series presented by Johnson et al. Meteor impacts and anisotropy of upper mantle rocks. Becker, 2019, makes the following points in respect to the dynamics of the upper mantle in light of seismic anisotropy. Anisotropy of upper mantle rocks records the history of mantle convection and can be inferred remotely from seismology. Seismic anisotropy refers to the orientational dependence of propagation velocities for waves traveling at different azimuths, or a difference in velocity for waves that are polarized in the horizontal or vertical plane, such as Love and Rayleigh waves, respectively. Anisotropy is a common property of mineral assemblages and appears throughout the earth, including the upper mantle. In the upper mantle, anisotropy can arise due to the shear of rocks in mantle flow. As such, it provides a unique link between seismological observations and the evolution of our planet. The following map of Australia shows the distribution of weak axes, that is, those with minimum flexural rigidity, delineating major geologic features such as the characteristic pattern over the Pilbara craton and others. Note that the anisotropy has a uniform or slowly varying direction that changes more abruptly over the Pilbara craton boundaries. Before proceeding, it is important to show the relationship of seismic anisotropy to mechanical anisotropy. Seismic anisotropy is revealed through seismic tomography, which allows the mapping of velocity perturbations in the Earth's mantle that indicate mantle temperature variation. Waves tend to travel faster in colder regions than in hotter regions. In the following maps, the thick blue bars are the fast axes, that is, cold material, of seismic anisotropy. The slow axes, that is, hot, would be orthogonal to the fast. The black bars are the axes showing minimum flexural rigidity of the lithosphere, that is, mechanical anisotropy determined using topographic and gravity data sets. The research by Kennett et al. 2004 shows the lithospheric structure in the Australian region. The blue bars are the vectors, the directions of fast seismic waves. The black bars, which are for the most part orthogonal to the blue bars, are axes showing minimum flexural rigidity of the lithosphere, that is, mechanical anisotropy. The black bar vectors were determined using topographic and gravity data sets. The thin black lines shown here were determined by Kirby and Swain 2006 and represent mechanical anisotropy. These thin lines were determined using gravity data that was analyzed using a two-dimensional wavelet transform. In the next few slides, the seismic, that is the blue vectors, will be removed from the map. We are left with a map of Australia showing the vectors of mechanical anisotropy and the direction of mantle flow. One can see there is a definite change in direction for mantle flow around and through the pink circle. That circle is coincident with the Pilbara craton, which Johnson et al. In 2022 proposed is an ancient meteor impact. Another location with disturbed mantle flow is the proposed Snilliquin meteor impact by Glickson et al. 2022. There are many other locations in Australia where there is an abrupt change in the direction of mantle flow. It is likely that each of these is an ancient meteor impact. Vortices and fronts present in the atmosphere and oceans, and comparable structures in the mantle. O'Driscoll, 1992, in his paper Elusive Trails in the Basement Labyrinth, presents evidence for such a possibility, where he compares vortices and fronts present in the atmosphere with comparable structures in the mantle. The formation of a vortex in the atmosphere, showing both cold and warm fronts. Two atmospheric tropical vortices in northern Australia. In support of O'Driscoll's possibility of vortices and fronts being present in the mantle comparable to those seen in the atmosphere is the research and conclusions presented by Bostrom. Bostrom shows that earth tide forces acting on a convecting mantle would cause the convecting material to rotate in an anti-clockwise motion in the southern hemisphere. Earth tide is the sub-meter motion of the Earth of about 12 hours or longer caused by moon and sun gravitation. These forces induce cumulative vorticity in an imperfectly elastic mantle. The biggest difference between convection in the atmosphere and convection in the mantle would be one of temporal scaling. In respect to time, within the mantle, convection would be measured on millimeters per year, where in the atmosphere it would be measured in kilometers per hour. Evidence of vortices and fronts in the Yilgarn Craton. Komatiites in the Yilgarn Craton. Moll et al. 2014 found that komatiites of particular ages occurred in essentially linear zones, as you can see here in this map of the Yilgarn. Komatiites become younger, moving from western to eastern part of the Yilgarn. Even though there is no data of ages within the Murchison domain on this particular map, generally the komatiites in the Murchison are older than 3,000 million years. The significance of komatiites. Quote, komatiites are rare. They're ultra-high temperature lavas that were erupted in large volumes 3.5 to 1.5 billion years ago, but only very rarely since. They are the signature rock type of a hotter early Earth. However, the hottest, most extensive komatiites have a very restricted distribution, in particular linear belts within preserved Archean crust. In the study by Moll et al. 2014, they used a combination of different radiogenic isotopes to map the boundaries of Archean microcontinents and space-time, identifying the microplates that form the building blocks of Precambrian cratons. This isotopic mapping demonstrated that the major komatiite belts are located along these crustal boundaries. Subsequently, the evolution of the early continents controlled the location and extent of major volcanic events, crustal heat flow, and, most important, major ore deposit provinces. There is another possible interpretation of the spatial distribution of the komatiites in the Pilbara-Yilgarn cratons. Here we have reconstructed the probable location of the ancient meteor impact through radial patterning of the Pilbara and Yilgarn cratons. Here we introduced the vortex formation in the atmosphere and taken the atmospheric low, superimposed it on the proposed site of the ancient meteor impact. Here the front is moving through the Narjar terrain, also known as the Northern Western Gneiss terrain. It is in this terrain where the oldest rocks known to occur on Earth were found in the Jack Hills, 4.4 billion-year-old zircons. 3,000 million years ago, the warm front would have been in the Murchison province. 2,900 million years ago, the warm front has moved into the Southern Cross province. 2,700 million years ago, the warm front would have moved into the Eastern Goldfields province. An example of oceanic vortex migration. Here we can see the formation of vortices in the Atlantic Ocean. Since the upper mantle, that is the asthenosphere, is a fluid, it's likely to have this kind of vortex formation as well. Again, the temporal scale at which the two processes exist would be very different. Giant gold deposits in the Yilgarn Craton. The gold deposits of Western Australia. The area of special interest mentioned previously in this presentation. And that area of special interest is Kalgoorlie, which indeed is one of the world's largest gold deposits. Even a casual glance at the spatial distribution of the gold deposits around Kalgoorlie shows a radial distribution. Radial distributions of this type arise from Rayleigh-Benard convection in the mantle. For a discussion of Rayleigh-Benard convection, see PowerPoint 6-1 titled The Golden Network in the Trunkie Creek Ophir Area, New South Wales, Australia, in our YouTube channel. Zooming in on the Kalgoorlie region shows the presence of two distinct radial centers. It seems likely that the circle with the radial pattern to the north migrated south during the opening of the Hamersley Basin. We can see here that as the center migrated, other radial arms of the center moved along the path of migration. This is indicated by the blue arrows. Note the three gold deposit clusters brought to our attention by the three broad arrows. Each of these arrows points at a cluster that is 10 to 15 kilometers long. Each of these spurs was created as the radial arm, indicated by the red arrow, migrated to the south. Weinberg, 2008, supports this speculation, this proposal, in his paper titled Extension and Gold Mineralization in the Archean Kalgoorlie Terrane. This is the current Kalgoorlie Super Pit and the surrounding town. The Kalgoorlie Super Pit, known as the Golden Mile, has produced approximately 58 million ounces of gold since the first strike by prospector Paddy Hannon in 1893. Previously in this presentation, it was proposed that an ancient meteor impact was centered on the Pilbara Craton. The outer ring of that proposed meteor impact was 1,800 kilometers in diameter and is represented here by the dark blue circle. It is quite possible, with the knowledge of the extension of gold mineralization in the Archean Kalgoorlie terrane, that the proposed meteor impact centered on the Pilbara Craton is only 1,500 kilometers in diameter, as indicated by the light blue circle. Some observations about the Kalgoorlie gold deposit. It is located on the circumference of a proposed ancient meteor impact. Many world-class metal, oil, and diamond deposits have the same spatial relationship to ancient meteor impacts. See the following presentations on our YouTube channel as confirmation for the claim that many gold, diamond, metal, oil deposits around the world occur on the circumference of ancient meteor impacts. Summary and contributions from our presentation titled Gold, Cratons, and Meteor Impacts. Even though the focus for this presentation has been on the cratons of Western Australia, they appear to be archetypical of the 35 cratons recognized here on Earth. The radial distribution of major faults in the Pilbara Craton continuing into the contiguous Yilgarn Craton indicate that the current size and distribution of these cratons are part of a much larger pattern. There is evidence that the larger pattern was created by a major meteor impact with an outer ring of approximately 1,500 kilometers in diameter, centered on the central northern western part of Australia. The Pilbara Craton is the site of that ancient meteor impact. Ancient meteor impact sites can be revealed through determining the anisotropy of mantle rocks. The bulges revealed by the faults in the Yilgarn Craton are caused by TTG, that is tonalite, trondhjemite, granodiorite intrusions. The bulges are the same size as the Zimbabwe Craton intrusions. Komatiites formed only in early continents and control the location and extent of major volcanic events, crustal heat flow, and especially major ore deposit provinces. Komatiites are common in the Yilgarn Craton. Vortices and fronts present in the atmosphere and hydrosphere have comparable structures in the mantle. Radial patterns indicative of Rayleigh-Benard convection are present in the Yilgarn Craton and relate to giant gold deposits. The giant world-class gold deposit at Kalgoorlie is proximal to the center of a radial pattern and on the outer edge, that is the circumference, of an ancient meteor impact.